When you talk about atomic structure and movement of electrons in an atom, the first thing that comes to our mind is the solar system model, right? So how does it look like? We have the nucleus where we have neutrons and protons. Nucleus is positive, and we have circular orbits around the nucleus where we have electrons moving around, right? So for a solar system model, these orbits are circular and the electrons are moving constantly. So we assume that we have equal number of electrons or almost equal number of electrons on the left and right side of the atom, right? That creates a symmetry. As we have equal number of electrons on both sides, there is no problem, no charge, no poles, nothing. It's an ideal scenario, but in real life this doesn't happen. What happens in real life is there are some spaces, 3D in the 3D space, where the probability of finding electrons are very high. We call those places orbitals. So in real life we have orbitals where the probability of finding electrons are very high. Let's say this is an orbit and we have places in there where we have the high probability of finding electrons. Now we know that electrons are moving constantly, they have fixed way of moving, right? Inside an orbital, the movement of electrons are random and they are moving at different speeds. Now because of that one, in an instance what happens is there are more electrons on one side than the other side. As we know that electrons are negative, when there are more electrons on one side, it creates a negative pole, and the other side, because of lack of electrons, it produces or creates a positive pole, right? Now it happens in an instance because they are constantly moving around. In the next instant it's possible that they get balanced again and they get imbalanced, and then again they get balanced. It happens all the time. So these dipoles are created in an instance. That's why these dipoles are called instantaneous dipole. Instantaneous dipole. Okay. Now that we have instantaneous dipole, let's consider another neutral atom on the other side. On the right side we have a neutral atom, and we have electrons that are currently balanced. Let's assume that they are balanced electrons, but because of this negative pole, negative electrons are pushed back, repulsed and pushed back to the other side. So the electrons that were in this side will be pushed back to the other side. Let's say we have this one and no electrons in this side. Because of lack of electrons in this side, we have created, or it creates a delta plus or positive pole. On the other side, because the electrons have moved to that side, we have created a negative pole, which is a delta minus. Now these two poles, the dipoles, are created due to the effect of the instantaneous dipole. So these dipoles are called induced dipole. Okay. Now we have opposite poles side by side. Now because of these opposite poles, there is a weak electrostatic attraction between these poles. This electrostatic attraction is called instantaneous dipole induced dipole forces. Instantaneous dipole induced dipole forces, that means the force between instantaneous dipole and induced dipole. This instantaneous dipole induced dipole is called the London forces. Now why are they called London forces? Because a physicist called Fritz London actually discovered this force. That's why it is called the London forces. And this is how actually London forces form between instantaneous dipole and induced dipole. Now let's talk about some general facts about London forces. First of all, the London forces are the weakest type of intermolecular forces. We know that we have London forces, permanent dipole-dipole forces, and hydrogen bonds as intermolecular forces. The London forces are the weakest. And then these are temporary fluctuating attractive forces. We already have seen that because they are created in an instance. That's why they're called instantaneous dipole induced dipole forces. But the next moment it may not be there. So they are temporary fluctuating attractive forces. Then we have these forces exist between all atoms and all molecules, regardless they are polar, non-polar, or whatever it is. They exist in all kinds of atoms and molecules. And the last one, this is the most important one. If we have non-polar molecules or noble gases, uncombined noble gases, atoms, London forces are the only type of intermolecular force. Now, what do I mean? Let's say we have a polar compound H2O. So H2 is polar. In H2O, we have all three intermolecular forces. We have London forces, we have hydrogen bonding, and we also have permanent dipole-dipole forces. But if I talk about a non-polar molecule, let's say nitrogen, N2, in nitrogen, and like nitrogen, all other non-polar molecules and uncombined noble gases, the only intermolecular force present is the London force. This is very important because it is actually unique to the London force, right? There are some factors that can affect the strength of the London forces. Generally, there are two main factors that can affect the strength of the London forces. First one is the number of electrons, and second one is shape of molecules. We are talking about basically the surface area in contact. So let's discuss both of them one by one with examples. Let's talk about the first factor, number of electrons. So when you have a larger atom, you have more electrons, right? So when you have more electrons, the electrons are further away from the nucleus. So when you have a larger orbit, the more electrons means a larger atom means you have more orbits, so they are away from the nucleus. So further away from the nucleus, that means the electrons are not tightly held with the nucleus. So the electrons can move easily, right? So it means that electrons are easily polarizable. So when you have highly polarized electrons, these electrons can create stronger instantaneous dipole and induced dipoles. When there are stronger induced dipole and instantaneous dipole, the London forces are stronger too. And due to these stronger London forces, boiling points can increase and also the state can change. For example, let's talk about fluorine, bromine, and iodine. We know that fluorine is a gas, bromine is a liquid, and iodine is a solid, right? Why? Because in fluorine is small atom, right? A small atom is a small molecule too. It has less number of electrons. In iodine, there are so many electrons. That means the electrons can be easily polarized, and due to easy polarization, the dipoles are stronger too, and stronger dipoles leads to stronger London forces. And the London forces are strong enough to hold these molecules in a lattice. That is why in room temperature, iodine is a solid, bromine, a little less strong London forces, is a liquid, and fluorine is a gas. Long unbranched straight chain molecules have higher or larger surface area to interact, and this, for this reason, they can pack together closely together, which creates a larger surface area to form the London forces, and the London forces are kind of stronger there. But when we have highly branched molecules, they are like spherical. We're going to see an example. But when we have highly branched molecules, they are kind of spherical. And because of this spherical shape, what happens is their surface area gets reduced, and in turn, they cannot interact in as many ways an unbranched molecule can, which makes the London forces weaker. Let's see one example. Let's say we have pentane C5H12. Now, normally C5H12, if we draw it, it looks like this, right? So we have this hydrogens in there. It's a straight chain isomer of pentane, and it does not have any branch, and it has a larger surface area because another pentane, it creates a long chain and straight chain which has more surface area and more places to interact. So one will interact with another, so the London forces are easier to form and stronger. But if I just look at a branched version, let's say we have this one, dimethyl propane. So in this case, we have a spherical shape, kind of spherical shape, right? You can just look at it and it will feel like that you have a spherical shape. What it does is it reduces the surface area. When the surface area is reduced, the London forces cannot form that easily, and London forces are a little weaker. And because of that reason, this guy, a little bit stronger London forces, has a boiling point of around 34 degrees Celsius. But the branched one, which has a weaker London forces because of the spherical shape and little lower surface area, the boiling point comes down to just 9.5 degrees Celsius. So when we have long straight chains, they have higher surface area, so London forces are stronger. When we have branched chain, it's spherical shape, surface area is lower, and they have really low boiling points. So this was all about London forces. I hope all your doubts are cleared and you also have the proper note for London forces. If you like this video, you're going to like the other videos too. Don't forget to watch them and subscribe for more contents. Thank you so much.